Hey, Sruthi, how's it going? So I'm sorry I screwed up by not deleting this meeting invite. This is actually the link. If you can use this one,
Okay, sure.
that would be great.
Yeah,
So
yeah.
I'll see you over in the
Great,
Zoom.
great.
Yep.
Sure.
Great. Bye. Okay. Hi, Sruthi.
Yeah. Hi.
How's it going?
Yeah, it's going good. Let
Nice.
me just switch my phone. Uh,
Sounds
can you
great.
hear me better now?
Yeah, it sounds great. The sounds
Okay,
perfect.
perfect.
Yeah.
Perfect.
Cool. I'm sorry I was a little bit late. I had a meeting run over. But that's all right. I just updated the main invite. Did you want to just test out your slides and make sure you can like that you
Sure. Yeah.
just throw them
Yeah.
up, and then while you do that, I'll just invite everybody in the
Sure.
just remind everyone that it's happening.
I think I still can't share my screen.
Oh, yeah, I forgot. You have I'll give you permission. 1 second. Okay, try now.
Mm.
Nice. Oh, your picture's not there, Sruthi.
Yeah, because I'm there on the video, so I didn't put mine.
All right, nice.
Yeah. Okay. Yeah. So yeah, I think it works.
Okay,
Perfect.
cool. So we'll give it a couple minutes here. There's a couple people that registered.
Mhm.
And so we'll give a few people a few minutes to kind of roll in. Usually it's like 5 to 10 people will sort of start rolling in.
Sure.
And then, yeah, we'll run it. I've already recording this, by the way. So the recording has already started technically, but
Sure. Yeah.
I'll edit all this out just you know, and then when I upload the video to the YouTube channel, it'll just be this presentation. And if you want to share this presentation, just send it to me afterwards to my email in
Sure.
PDF
Yeah, I can
format
share it.
yeah, in PDF format or whatever, and then I'll upload it as a slide share and I'll put the link in the video description.
Yeah, sure. Perfect. I'll do that. Yeah.
Cool. Awesome. Yeah, so let's maybe give it, I don't know, a few minutes, 5 minutes or so, and then we'll plan on starting maybe just 10 after.
Sure.
So
Yeah.
if you need to get like a water or just get prepped at all, just yeah, feel free. And then yeah, and I guess Lucas, welcome. So we'll get started in a few minutes here. Yeah, so Sruthi, just so you know, oh, I two things actually, housekeeping items. So do you prefer questions throughout or at the end?
Throughout is good. I think
Okay.
it's like it's great if like there is something and people ask me right then. I think it just clarifies things. So throughout is great.
Okay, great. And then
Yeah.
um the the chat. I'll read you questions that come in the chat, and because I'm not sure if you have
Yeah.
two monitors or not, so sometimes it's easier for me to just read the question. So if someone types
Yeah.
questions, I'll let you yeah, I'll just read the question aloud.
Yeah,
Um
that would be great. Yeah. Thank you so much. Yeah, I don't have another monitor right now. Yeah, so that
yeah,
would be great.
no worries. Okay, so we'll do that, and then yeah, people like I said, the way these things usually work is like the peak attendance is around 45 minutes in, and then it's
Mm-hmm.
like a mountain, so it's like people like start coming in
Yeah.
and then they start going out. So people will filter in and out. Typically
Sure.
we usually have a handful to start, and then it'll pick up over time, but we'll give it 3 minutes. We'll kick it off. I'll introduce you. By the way, it's just so I know,
Sure.
or so I want to make sure I pronounce your name right. Is it Sruthi?
Yeah.
Okay.
That's perfect. Yeah.
Okay. Sruthi Sekar or Sekar?
Yeah.
Okay.
Sekar is yeah,
Sekar. Okay.
closer.
Sruthi
Yeah.
Sekar. Did I say that
Yeah.
right?
Yeah, that's perfect. Thank
All
you.
right. All right. I'm sure it's not perfect, but I'm going to try. um,
Yeah.
cool. All right. So I'm going to go get some water and
Sure.
yeah,
Yeah.
and
Yeah.
and I'll be right back here. I'm going to put another reminder in the channel, and then we'll get things kicked off here in about 3 minutes.
Sure. Yeah.
Cool.
Sorry to interrupt. A colleague of mine asked if there's a direct link or so that he doesn't have to register.
Oh yeah. I put it in the here. I'll you should be able to just get the link. I don't know if you guys can get the link here. Let me put it in the messages or in the chat. There's the link. It's in the link is in the Telegram too. I think if you're not, but I'm not sure if you're in the Telegram. But yeah, there's the link. Feel free and share it with anybody.
Thanks.
And yeah, here, let me turn my camera back on here and let's get things kicked off. All right. Okay, cool. So I'm going to kind of give like a 3 countdown and then I'll edit all this out and I'll introduce you quickly, Sruthi, and then I'll let you get started. Okay. Hello, everyone. Welcome back to another edition of zkStudyClub. Today, we're very proud and excited to welcome Sruthi Sekar from UC Berkeley. And she's got a new paper called zk-SaaS, Zero Knowledge SNARKs-as-a-Service, with colleagues shown on the slide here. But we're very happy to welcome Sruthi today, who's going to present this work. Sruthi, thank you for being here.
Yeah, thank you so much for inviting me. And I hope to tell you more about your work. And feel free to interrupt me at any point during the talk. So yeah, let's hope I get to tell you more about Zero Knowledge SNARKs as a Service, or zkSaaS as we call it. So this is joint work with Sanjam Garg, Arushi Goyal, Abhishek Jain, and Guru MC Policharla. So before we head into, what is Zero Knowledge SNARKs as a Service, just as a recap for everyone here, what are zk-SNARKs? So they are these primitives that help a party call a prover, prove an NP statement of this form, which is, that there exists some witness for which, this relation circuit outputs 1 if it's a valid statement. And this proof is sent to this verifier, who then accepts or rejects it. And the verifier has only access to the statement and not to this additional string called the witness. So it requires some additional properties, and it comes, that's what is represented by each of the adjectives in the name. So zero knowledge means here that, the string W that the prover has in addition to give the proof itself hides that W. So that's what on a high level zero knowledge means. Succinctness is something that's desired for applications, which is that as a verifier, I should not be required to do too much more computation, or rather like the computation time to verify should be much less than, actually just evaluating the relation circuit. So that's what succinctness here means roughly. Non-interactivity is something that's already depicted in the picture, which is that it's a single shot proof and anyone can essentially verify. And soundness, again, I'm not explicitly stating what arguments of knowledge is, but soundness roughly means that, the proof will not be accepted if the statement is not valid, which means if there is no witness such that this holds, then, prover will not be able to prove a false statement to the verifier. So that's like, a high level recap, which probably people here would already be familiar with. And not surprising, zero knowledge SNARKs, specifically with the zero knowledge component, have also found numerous applications since their use, which includes anonymous credentials, verifiable inference of machine learning, private smart contracts, proving the existence of bugs in code, or security vulnerabilities, fighting disinformation, which I'll talk about a little bit in detail as a running example, and private transactions like Zcash. So, no wonder that we have several such applications where I have listed out specifically the ones where zero knowledge is also needed. No wonder there has been a flurry of research in, improving the efficiency of the SNARKs in terms of like all the parameters, including, keeping the balance between succinctness and provers running time. But unfortunately, for several applications, and I'll state a running example to show you what I mean. The prover time in generating the SNARKs still remains to be much larger than the relation circuit time, and this for certain applications, at least, picking out any of the general SNARKs from here doesn't serve the purpose, and it still turns out to be very inefficient. And here is a running example to kind of elaborate on what I mean. So the example is that of fighting disinformation, which is something that has been recently, shown to have like a very deep impact, and is one of, an important application to look at where zero knowledge SNARKs serve, they can be applied to. So particularly here is an example where a prover has some video clip. So this could be about images or about video. But let's say, video, because it's like a larger file. So the prover is trying to prove that, only an allowed set of edits have been made to this video. And this is important to do so because while camera these days come with, some form of signatures with which you can authenticate the image that has been clicked. However, when you see like these images or videos circulating online, you do not have control over like what software was used to edit and what kind of edits were made. So in some sense, like the already existing like signature would not work for you to authenticate it. And particularly some of these images or videos might be sensitive, which is where the zero knowledge aspect comes out to be important. And you may have like edit operations, including blurring sensitive part of the image or video. And zero knowledge SNARKs help out in such scenarios where, as a prover or as a person publishing the video or image, you append a proof that, only a certain allowed set of edits and nothing fishy was done to this video or image, and hence you can trust it. So as a verifier or as a viewer, you can just check that it's a valid, image or video, and then like believe it. So that's the rough idea behind, how you would fight disinformation using SNARKs. So as I said, the prover would send this proof proving that only a allowed set of edits have been made to this, video. And clearly the proof needs to be zero knowledge because, there are sensitive parts of the video, and in proving something about it, you don't want to leak those blurred out parts or those sensitive parts. And clearly here, when you consider the example of video, typically all the videos, even shorter clips, if it is high definition, it's going to be super large. And so if you pick out any of the SNARKs, as is, the generation time is going to be super long. So this is going to be, a running example for you to understand that there would be scenarios where the relation circuit that you're trying to prove can be like really large with, a large number of gates. And for such scenarios, a single prover doing the entire proof computation can be really expensive. And so the question that we ask is, can the zk-SNARK computation itself be delegated instead of a single prover doing it? So, of course, like, here's a simple thing that all of you might already see is not a good enough solution. What if we just, send the video to a powerful machine and then ask it to compute? So just delegate it to a single server of sorts. Of course, okay, that works. You can get the proof and the prover doesn't have to do the work. You've completely delegated. But this violates privacy because you're just giving the entire witness to the server. And it's not just that you're protecting the sensitive video from the verifier, but you also want to protect it from the server that you're delegating this to. So this is not a good enough solution for the setup that we are looking at. So instead, what we ask is, sure, okay, we delegate this to a bunch of servers instead. And you don't give the entire witness to all these servers, but give them in some form in which each of them do not learn anything about the witness. So as we'll see later, it's like giving a share of the witness, where each of the share doesn't leak anything about the witness. And the group of servers will, using this shared witness, just run a multi-party computation protocol, which is just a protocol that helps you, generate the SNARK proof without revealing anything about each other's secret inputs in some sense. Okay, so this is the rough idea where we visualize the delegation to be useful, and it's not just us. This concept was like formalized, into a concept of T-server zero knowledge by this work of collaborative zk-SNARKs by Özdemir and Bone in 2022. And that brings me to a comparison of what was known, right? So we did want to do it, but it's not so much that this was not done in some form before. So the collaborative zk-SNARK work does formalize this notion of how to, do an efficient MPC to compute the zk-SNARK proof while still preserving the client's witness. But unfortunately, each server in this multi-party computation takes as much compute time as a single prover. So this is good for like, wanting to do this delegation in a private way, where you might not be looking at applications essentially where the circuit is like super large. Maybe a single prover itself is good enough, but it's just that the client who is wanting to do it does not have that much compute power. For such scenarios, collaborative zk-SNARKs is itself great. But remember, our running application is a scenario where the circuits are like super large, and necessarily single prover computation time may not be good. And on the other side, there was this work of distributed zero knowledge proof system, or DZIC, where they did look at how to distribute the work the prover work across several machines in a compute cluster for faster proof generation. However, they did not care about the privacy aspect. So essentially all the clusters that you're using will get the entire witness. So there's no privacy component ingrained in this. And our result somewhat tries to combine, the best features from both of these works, which is get the faster proof generation by, delegating it and actually getting a divide of work amongst the servers. And at the same time, preserve the privacy guarantees that the collaborative zk-SNARKs work did, which is you also retain the zero knowledge, not just against the verifier, but also against the malicious servers. Okay, so with that, we required, here is a very brief summary or a roadmap of what we end up doing. So the first step we do is formalize this framework, and that's what we called zk-SaaS or zero knowledge SNARKs-as-a-service. And the goal really is to make this useful, where you provide or SNARK generation as essentially a service where a client can come, give you its shared witness, and then request you to give a proof, and be sure that nothing about its witness is going to be leaked in this process. So this is what we formalize, and each server here, I want to stress again, each server here is expected to run for a shorter duration than a single local prover. If not this, then it's essentially collaborative zk-SNARKs where you take as much time as a single prover. So this is a key expectation we have from this framework. And then we go ahead to design the zk-SaaS for some of the existing, widely used SNARKs like Groth16, Marlin, and Plonk. And these were also the choice, SNARKs in the collaborative zk-SNARKs work. And we show that you get faster runtimes than local prover. So specifically, we have a prototype implementation where we show that, zk-SaaS we show it for Groth16 and Plonk. And we get a 22x speed up when you run with 128 servers. And I'll talk more about, what is the compute power, memory power that you need from the servers. But this is the, just a summary of how much speed up we end up getting. And we can go up to 2 power 25 constraints for Groth and 2 power 21 gates for Plonk. So this is the summary of our results in some sense. And I'll compare it with our concurrent work, which is, EOS, and in the next slide. But, if anybody has any questions about this, would be.
I was actually going to ask about that EOS, because EOS is obviously Pratyush's work, right? So I think
yes.
Berkeley alum. So I was curious to hear the comparison with that. That was my only question up to this point. Does anyone else have questions? All right, yeah, keep rolling.
Okay.
This is great.
Perfect.
Thank you.
Yeah. So this is the point where I bring up this concurrent work. And of course, their goal as well was, private delegation of zk-SNARKs for faster proof generation. But I just wanted to highlight there were certain differences in their model from ours, which comes from the kind of, again, the underlying theme is similar, where MPC is used to do the proof computation, and you do it in a fast, efficient way to make it useful. But the highlight is the difference in the model. So in EOS, what you require is for the client to be always online. So in some sense, I think Pratyush already spoke about this, that to make use of or to actually get gains in the runtime, you need to also bring in the delegator or the client. They call it delegator. So the client always needs to be online through this MPC computation of the zk-SNARK. So you do an MPC where the client is the honest party. And in this model, the goal is to reduce the client's work, right? So it's not so much that you visualize the client just coming, giving its witness to the servers, and then now the MPC is done by the servers who then give it back to you. So it's not visualized as entirely being able to divide and split the work amongst all servers. Whereas what we visualize it as here is that the client really is not part of the protocol. And it's really application dependent scenario. If for certain applications, you're okay with your client anyways being online, then EOS is great. But in our scenario, we visualize, there might be async issues and things like that. So the client may not want to remain online. It can just come, do this like one-shot computation, give the servers the shared witness, and after the entire computation is done, the servers will return the proof to the client. So we really view it as a complete delegation of the work to all these servers. Besides that, in the paper itself, EOS has malicious security. They don't lose out on that. Whereas for us in the paper, we only prove semi-honest security for the setup. But I want to mention that we can add malicious security with just like a factor 2 speed up if it's Splunk. And in fact, for certain settings that are interesting enough for applications, I'll mention, later in the talk towards the end. For certain scenarios like Groth16 specifically, we can add malicious security without any additional cost. So we have zkSaaS for Groth16 with malicious security without any additional cost. This is something we can do. And we don't have this in the paper. We only present, semi-honest security for ease, but this is something that can be done. This is something just I wanted to mention.
Nice. And I guess, is it worth, I mean, you may do this in a minute, but I guess, is it worth defining what semi-honest security is in this setting?
Yes. So semi-honest security is where the servers can be corrupt. Two of them can, of course, be corrupt. But the semi-honest assumption is that they still follow the protocol. So whatever the multi-party computation protocol requires them to do, they would still follow the protocol. And this is typically the assumption in semi-honest adversaries. Whereas in malicious security, they can arbitrarily deviate and do whatever. And so for several practical scenarios, that's like usually the requirement that, you don't assume that the adversary behaves honestly. So it can do whatever it wants.
Gotcha.
So that's the, I would say, difference between EOS and our work. But again, like these model differences and stuff, it really depends on the application scenario and what kind of underlying secret sharing scheme or underlying stuff that you want to build and what you're more comfortable with for the specific application. It really depends on that, whether you use EOS or zkSaaS. So that's really the comparison that I want to leave at. And if you have any more questions,
No, this is great. Yeah, I agree. I think it's right that I think like a lot of these schemes, like on their face seem similar, but I think there are important differences. And I think the specific application matters. I mean, obviously for the purposes of zkStudyClub, it's all about research. And, obviously this research is typically focused on pretty low level protocols, that people build on. But I think it is important to think about it from the other side where to your, we were just talking about security, right? Like in the practical setting, is anyone going to be okay? Or is semi-honest security enough? I mean, probably right, for some applications, maybe not for every application, but I think that's the key. So it's great to have a greater diversity of these different models that people can build upon because it theoretically supports a greater class or more applications. Right. Yeah, no, this is great. Thank you. Yeah, let's continue.
Actually, we can also add the malicious security, but it comes at the cost of a factor 2 blow up in the prover time.
Cool. Yeah.
And but it's like, whether you're willing to pay the price.
Yeah, exactly. Yeah. Depending on the application, of course. So yeah, let's jump into it. And I think it'll be interesting to see, obviously the concrete, seeing concretely, like, how some of these advantages manifest. So yeah, thank you, Sruthi. Please continue.
Yeah, great. Yeah, so moving on, I'll tell you more about now the framework itself. So how do we build this? For that, let's take back a step and look at what does typical zk-SNARK computation involve. And today, I'm going to be in the setup of pre-processing zk-SNARKs, where there is some setup phase and you establish some common information. So the typical zk-SNARK computation involves a first step of computing something called an extended witness. So you're given this witness string and the relation circuit that you need to compute, or you're proving things about. And from there, you need to do this computation step of something called an extended witness before you go ahead and generate the proof itself. And the generating the proof itself has typically two sets of operations, and this is for a particular class of SNARKs. This is true. Where there are cryptographic operations, by which I mean, you have group exponentiations or pairing operations, and they are typically more heavy as compared to the field operations part. And this is typically, the very, very high level blueprint of what goes into a SNARK computation. So in our model or framework, what we want is for the client or, the person who's delegating the proof to come in and compute step 1, which is, computing this extended witness, and then secret share this extended witness amongst all the servers, right? So note here that the client already is doing, when you're secret sharing and sending the witness to all these servers, the client is already doing linear work, but then it's only in the field operations. So and also this component can be something, if you don't want your client to do, you can think of doing this component also by using some MPC protocol. So this part of the stuff is not something that I'm going to get into for how to do, but it is, of course, an important step to figure out for end-to-end implementation. And it really depends on what power your client has and, for the specific setup, whether you're willing for the client to do all this or you want to actually, get a split of work in that component as well. But I want to stress here that this aspect is all field operations, and that's why it's okay for the client to do in some sense. And then the servers essentially compute the step 2, which is generating the proof part. And of course, can use some additional pre-processing where each server gets some correlated randomness. And this is going to be, the step 2 is the part that we want the actual work divide. And step 2 generation using these servers is what would be the focus of zkSaaS framework, essentially. Okay, so, and within this, I want to stress that the more heavy computation, which is the cryptographic operations, they get equally divided amongst all servers, both in the sense of like the memory usage as well as the, compute time. And this is great. This is what leads to the saving that we end up getting. Unfortunately, the, end goal was to get a split of everything for all operations that you do, the entire proof generation. But because of a certain component of proof generation, which I'll talk about, and this is specific to the SNARKs that we focused on, which are the univariate polynomial regime SNARKs like Plonk or Marlin or Groth. The reason because of that, the field operations unfortunately do not get divided entirely, and there is some asymmetry in the server requirements that we need. So we need one of the servers amongst all of them to be, some king server that is able to do linear in the number of field operations. But the remaining servers can all be like much smaller machines. And because the field operations also get equally divided amongst all the small servers. So this is unfortunately the asymmetry we still have in this model. But in spite of this, because at the end of the day, the king server needs to do linear work, but only in the field operations, and the heavier cryptographic operations get divided, we see like still a large improvement in the number. Like as I mentioned before, we get a 22x improvement than what a local prover does. But of course, like the dream goal is to, get to a zkSaaS framework for something that, this kind of asymmetry also doesn't exist.
So this is like a direction for future work, is to figure out how to reduce
exactly
the asymmetry. Got it.
Yes, so I'll particularly talk about like what is the protocol also that needs it. Looking ahead, it's essentially FFT. So when you're trying to do this split of work amongst all servers and figure out some distributed protocol for FFT, that necessitates such an asymmetry in some sense.
If you were
I'll talk about it.
If you were using a different type of zk-SNARK that didn't require the computation of FFT, like I think I recall correctly, like Spartan, I believe, does not require FFTs. Would that how does that change in this model? I don't know if you guys
that would get a perfect, that required work to do it, but we have some follow-up work we're working on it essentially. So essentially, non-FFT based SNARK will not have these issues that we face specifically for FFT. And the remaining computations are all nice. So MSMs, which are the more heavy part, they get completely divided, as I'll show you. Yeah.
Right. And I guess maybe on the flip side, a SNARK that is heavy FFT, like STARKs, for example, would be, it would probably be the disadvantage. This model would be more disadvantageous for those categories of SNARKs. Is that, would you?
Right.
Okay, got it.
Yeah. So I do want to point that even if you get, that improvement in number because, you end up that the group operations dominate, but not for the example you mentioned where anyways group operations may not be there. But the main thing is that we're, in some sense, look at it this way, that because of this one requirement of asymmetric need from a king server, you're still, in some sense, in the memory requirement, somewhat restricted by what the underlying SNARK is restricted by. Not so much, we can still tolerate, a little bit more in the sense of constraint size or gate numbers. We can go a little bit above what the local prover does, but not so much, not as much as we would like to, because of this asymmetric need. So this one king server really hinders that in some sense. So it would be nice to get like a full split, and who knows, we'll be able to go all the way up to like 2 power 40 constraints or something, which is not possible in the local prover for sure.
Yeah.
So
cool.
Yeah.
Thanks. By the way, if anyone else has questions besides me, feel free to jump in, but I'm just a curious person. So please continue, Sruthi.
Yes. Yeah, feel free to interrupt me anytime. Just I want to mention again. Okay, so what are the kind of example applications where such a framework might be useful? Like I listed a couple of examples of, where zk-SNARKs itself are applied, but I just wanted to bring it back with the model in mind. And you can have like two sorts of things. One, on the one end, you might use this application of SNARKs as a service to aid users with mobile devices who do not have as much compute power. So particularly there may be, these two applications of private transactions and smart contracts, where you're trying to prove general computations on smart contracts, or you might have like statements involving Ethereum wallets. And essentially the vision is that, as a mobile device, you can just send this to all these servers, and, not even required to be online while they're computing things for you. And then you will get back the proof essentially. So that's the vision for this side of applications. The other is something I spoke of as a running example, which is when you consider computations or SNAR, where the SNARK prover anyways does like really huge computation. So for extremely large computations like fighting disinformation will have, or even verifiable private machine learning inference, because the learning model is what determines how big the circuit is. For such scenarios, again, like this will be useful because you would be able to get a divide of work amongst all these servers. So the burden is reduced essentially. Yeah, so heading into how do we design zk-SaaS? So I hope like everybody's on page with how the framework works. The blueprint of the design is something similar to what was done in the collaborative zk-SNARK work, which is identify the key building blocks in the underlying SNARKs that we're interested in. So as I mentioned, we'd be interested in Groth 16, Marlin, and Blanc. And then we focus on designing, these MPC protocols for these underlying building blocks. And now there is an additional goal, which was not a part of the collaborative zk-SNARK. We also want the desired efficiency. So it cannot be just an MPC that runs on, the regular shares and does the same amount of work per server as the local prover. We actually want a protocol that, we actually want a protocol that gets a divide of work amongst.
I just saw
all the servers.
the king server just pinged you. I see right there with its updater request. Sorry, bad joke, but
yeah.
Anyway,
Sorry. Yeah.
Go ahead.
Yeah. So so you basically design MPC protocol, but now with this added efficiency requirement that you have to also get a divide of work amongst all the servers or all the parties. And once you have these two, like essentially you head into essentially stitching all of them together. And if it is a IOP protocol like Blanc or Marlin, you need to figure out how to do the Fierchamir step. And then you get to essentially the zk-SaaS for SNAR. So I'll not talk about the whole picture, but
all right. Sruthi, I think we lost you there. That possibly was me. Hopefully it wasn't me, but we're still recording.
Yeah.
So you want to just present again, Sruthi, and do
Sure,
us
sure,
pick it up
sure,
right where
sure.
you left
Yeah.
off. Sorry about that. If it was
Sorry.
make sure my
Yeah,
network's
sorry.
clear.
I'm
Great.
so sorry.
Awesome. All right.
Let me minimize this. Perfect. Okay, yeah, sorry about that. I don't know what happened. Cool. Yeah, so I guess I was just talking about the basic blueprint. I was going to say that essentially I'm not going to talk about the full stitching image, but I just want to mention, in case you're wondering, how the Fiat-Chemie step would be done in the case of like Plonk or Marlin. You don't do the computation of the hash. So, I mean, before that, just what does doing Fiat-Chemie mean? Like if you're in the IOP setting where you're building an interactive protocol, public coin interactive protocol, and then converting it to a non-interactive by essentially making use of something called a Fiat-Chemie transform, you would be requiring to do some hash computations or random oracle computations on the transcript to essentially compute the verifier challenges. And this step you don't do inside the MPC. So I want to mention here that you build essentially the MPC for each of the blocks separately. And whenever you need to do, this Fiat-Chemie step or computation of the hash, you end up, if you're in the semi-honest setting, nobody deviates from the protocol. So you can get one of the servers in this setting, since there's already asymmetry, all the parties can send their shares to one of the servers, and in a hidden form, of course, because the zero knowledge also has to be retained. And the single server can do this hash computation and then, send it back to everyone. So the Fiat-Chemie step is something that you don't do over the MPC. You do it outside the MPC. You do the reconstruction and then compute it. So that's something I want to mention of how you would convert it into the fully non-interactive version of Marlin and Plonk. But besides that, rest is just like once you have MPC for each of the building block, you're good to go, essentially. You can just plug in that MPC and, you can use it with underlying SNAR. Okay, so that brings me to what are the building blocks in these SNARKs that we're interested in. So essentially, they're comprised of these 4 operations. Once you have these 4 functionalities, you can do the SNARK proof. You can generate the SNARK proof just by making calls to these functionalities. So of them, there's only one of them, multi-scalar multiplications or MSMs, which involves group operations. So it's essentially you have M group elements and M field elements, and you're required to do this kind of a product of the group exponentiation. Remaining all the operations are field operations. So particularly we would require something called partial products, which is specific to Plonk, where you require to essentially, as the name suggests, compute partial products of all these field elements, all the partial products. And besides that, if you're in the setting in any of these SNARKs, you would be required to do computations on univariate polynomials. And specifically, you need FFT for converting between what is known as the coefficient representation and the evaluation representation. And that is what ends up making polynomial multiplication and division faster. So this is something that you would also need if you're in this setting. And that's pretty much it. So these are the operations for which we need to be able to design this distributed protocol or an MPC that essentially gets this divide of work. Okay, so that brings me to what is the key primitive we use to do this. What is it that enables us to get this divide? And that's something called PAX secret sharing. So before I highlight what PAX secret sharing means, let's start with something all of us here might have already seen in some form, which is regular secret sharing. So what is the goal in regular secret sharing? There is a single message, a secret value, which you want to split amongst these n parties, S1 through Sn. And, we represent it by this in future, just the square braces around n. And the guarantee here is that if you're in the semi-honest setting, as I've been saying, the corruption threshold, by which I mean how many of these parties can actually be adversarial, or how many of them can be corrupted by an adversary. That can be up to n by 2. So up to half of them can actually be corrupt, and you can still hope to protect your secret against them, right? So what this means is T of them cannot learn anything about your message M, whereas if you get T plus 1 of them together, you'll be able to reconstruct the message. So this is what regular secret sharing gives. And the most commonly used regular secret sharing scheme is for the threshold setting like this is Shamir secret sharing. This is something that we would have seen. But extending on from here is what is pack secret sharing. And this also can be very easily built from, Shamir secret sharing. And what it helps you do is, instead of just secret sharing a single secret vector in a single secret value, you end up secret sharing a vector. So you now combine M1 through ML, L values, and together you share them into these secrets S1 through Sn. So what you're doing is, instead of just splitting one value into these n shares, you can go all the way up to some order of n, just like some constant factor of n values can be packed together, and you can share them together. And the trade-off here is, of course, with the corruption threshold. So this cannot be unconditionally done. It's that whatever you choose to pack together, the L will determine how much you can tolerate in the sense of corruption threshold. So this is the relation that will hold now, which is, combine the number of parties you choose to corrupt, T, plus the number of values you choose to pack. That is now like at most n by 2 in the semi-honest setting. Right? So this is something that you would have to tolerate as a trade-off. It's not an unconditional thing. Why is this useful? On a high level, like when you pack all of these things together, what you end up doing when you compute anything on the shares will be a combined effect on a vector of values instead of a single value. So as I'll head into a bit later, the idea is that now you're combining the computation of several values by packing them together and reducing it to just doing computation on these shares. So packing will essentially help us get the reduction or the split in the cost the way we visualize.
Got it. So is the way to think of this is basically pack secret sharing is just a vector as opposed to a single value.
Yes.
Point. Okay, got it. Great.
Yes. Yeah. Perfect. So just to, how do we compute on the pack secret sharing? So if you have like these two vectors, U and V, and they're pack secret share into, let's say, 5 shares, then addition is like simple. If you add the shares, the corresponding vectors get added. So this is how addition will work. Multiplication will now be a Hadamard product. So in regular shares, we already know that multiplication to do degree reduction requires some communication, which will be the same here. But the only difference is, because it's vector of values, it's essentially a Hadamard product. So if you multiply the shares, correspondingly, you get a Hadamard product of the corresponding vectors. And this is now a 2T out of n pack sharing. So if you want to bring it back to a T out of n, which means T is the threshold of the parties that can be corrupt, then you need to do some communication to do it. But this is like similar. So I just wanted to highlight this so that you're able to visualize how to do the computation on pack secret sharing. So addition is going to be local. Okay. Yeah. So with this now, we're back to the goal, and this is all the building block that we need. We can focus again on looking at these operations and trying to do a distributed protocol for them. So I'll start with the most heavy and the most important component that helps us get the speed up, which is the MSM part, the multi-scalar multiplications. So this is the function as I mentioned before, and the GIs are the group elements. So the key observation here is, how do we secret share group values? So whatever I spoke of right now as a value, I meant those are field elements, and regular secret sharing or pack secret sharing, all of them focus on sharing field elements. Like Shamir is something that works on only field elements. If you take other secret sharings, you can make something work for group, but in the setting of using Shamir secret sharing, the key observation that was made by this paper of collaborative zk-SNARK is that if you have to share a group element g power x, what you can do is just compute shares of X, which is in the field. And then you exponentiate each of the share that is received using the same generator G. So essentially you visualize sharing group elements as just sharing their exponents. Okay, and this will be of great use in the MSM case, as we'll see just in the next slide. So we can just extend the same thing for pack secret sharing. There's no surprise that instead of just computing shares of, this vector of group elements, you compute shares of the underlying exponent vector, and then you can just exponentiate the shares that you get with the same generator G, and that will be the secret sharing for the group. Okay, so this is what we have when I say the group element is shared. This is what we would mean. Okay, so with that in mind, let's take an example scenario. Let's say there are 32 values, so M is 32, and it is our choice as to how much we want to pack together. And as I said, this is like a trade-off thing, and we'll see in implementation what is a parameter that's reasonable to choose. But for now, let's say I'm packing 4 values together, by which I mean the L in the pack secret sharing is 4. So let's say this is the order in which I pack, and this is something up to us, like how we want to put these values together, and that depends on the computation you want to do on them. So here, like for MSM, you can essentially just pack them in a sequential order, G1 to G4, G5 to G8, and so on. So you pack secret share, these group elements as well as the field elements. So all the inputs are shared now. Okay, and now the key observation, because of how this secret sharing of the group element has been done, is that if you observe here, while this is a product of group values, it essentially ends up being a linear operation on the exponent, right? So this is something the parties can locally compute initially, which means if you have these secret shares, they can essentially just do a local computation and essentially receive pack shares of the single vector, where if you really look at it, when you're multiplying all of these group elements together, the corresponding first entries of each of the vector, you're doing a MSM computation on that. The second gives the second value of this vector, the third, and fourth the fourth. Does that make sense? Like you're just doing essentially this local computation on the exponent because you have the shares corresponding to it. And this is something the parties can locally do on the shares that they have. Right? So on the shares that they have, they can just combine these values in a like it's just a linear combination. So addition on shares is like local, and you're doing it on the exponent. But
this is where the trade-off comes in, I guess, where if you
this is where the trade-off comes in. Exactly. Yeah. So instead of doing this product of M group elements, you have like managed to pack them together and reduce it to just doing M by L. So you're getting a split by L. L is 4 here. But whatever L you choose, you're essentially reducing the work by that. This is not the end of it, by the way. Like, so here we ended up with a single pack share of this vector. But to, in a sense, complete the computation of MSM, we need a product of all of them as well, right? And this is something now you can't do. You've arrived at a scenario where the single pack share has everything, and you need to do a computation within the share. So that's something you won't be able to do. And so there's an easy way out here, which is to convert them into regular shares. And this conversion is something that can be efficiently done. If you have a pack share of a certain vector, you can convert them into these regular shares of each of the components separately. So each of them you split, and then now you can do the same local operation, but now on regular shares. So you can essentially get the final output, which is a product of all of these together. Yeah, so this is like, a high level of how you would do an MSM operation if you have the power of pack secret sharing, essentially. And so the factor of, as Alex, you mentioned, the factor by which you get the divide and work is essentially the packing factor. And so whatever L you choose, you're going to get a divide and work by that for the scenario. And it would also be, it will be the divide also that you get of the memory use.
Cool.
Okay. So this is the good part. Like MSM is something you get full divide on, and that's great. This is what gets us the speed up. Partial products is something that I won't be talking about today. It's something similar to this, where we managed to get the divide, and it's something very specifically needed for Plonk. So for that, you can look at the paper. But what I wanted to stress and spend some time on is the FFT part, because this is the component that
if I can just interrupt and ask a quick question, if you go back one slide.
Yeah. Sure. Yeah.
So this is like in the picture you showed, this is like, oh, this is the normal servers, not the king servers, right? So the normal servers.
Yeah. Normal servers can do.
Right.
Yes.
And then another FFT is what the king server, quote unquote, king
exactly.
server is doing. Basically, got it. Okay.
Yes. FFT is what necessitates the king server, or like this asymmetry is because of FFT. And so that's what I wanted to spend some time on, and make it a point like this is a problem with this particular algorithm. So if zkSaaS were to be built for something that doesn't use, you may not have this issue essentially. So, just to recap, FFT is something, again, like all of us might be familiar with, but just to put it in context of what is the form in which we look at the distributed protocol. So what is the goal of FFT? You have this polynomial in, coefficient representation where this AIs are the coefficient of the polynomial. Let's take a degree 31 polynomial for use case. And we want to evaluate it on a bunch of points. So typically a polynomial of degree n can be represented in the form of evaluations by taking 32 points. So if it is a 31-degree polynomial, you evaluate it on 32 points. And for FFT, the specific set of interest are these roots of unity because of the nice properties they have. And essentially, that's what helps you get the speed up in FFT. And if you were to naively do this evaluation, you will take, cost. If it's an n-degree polynomial, you take n squared time. And what FFT helps you do is get it down to n log n. Okay, so on a high level, it's a divide and conquer process where you just split the polynomial at each level into odd coefficients and even coefficients. And then the way you look at combining them is by this equation where you just evaluate the odd and even polynomial on the value x squared instead of x. And this equation helps you get back an evaluation on P. Okay, so why am I like recapping all this, 101 algorithm stuff? It's to point out that, whenever you need to evaluate this polynomial P on the set W of roots of unity, instead you've now reduced by the single step into evaluating the even and odd polynomials, but now on W square. And because of how roots of unity are, the W square essentially leads to just 16 unique values instead of 32. Okay, so what ends up going on in FFT, you recurse this and go on all the way up to where, you split it and strip down into linear polynomials and then go back up evaluating each layer, essentially using the same recursive formula. So in this example, you will go for up to 5 steps and then end up computing, from this level 5 up down. So it's important to just visualize this to, understand how the packing is done. And that's why I'm going into the painful details of how FFT works. So I don't want you to look at it as a whole, but just this is just an image I had, to highlight what is the computation or how it's done across layers. So as I said, level 5 is where you strip down and essentially bring it down to this coefficients. So A1 through A32 are the coefficients of this polynomial. And from there, you have to do this, evaluation down each layer until you get essentially the evaluation representation on W. Okay. And the way it's done was the formula that I depicted before, but in a sense, what is it that's happening? So if you just focus on level 4, we won't get into the details of the remaining, but just to highlight the pattern here, which is what we'll use to pack things together, right? Is that all the left or the green highlighted values here get combined with the red values, which is the right of the right child, on the right side of the root. These values get combined using this sort of a linear equation. And the two sets of, scalars that you use for it are the essentially 2 points of evaluation that you're required to do. So for level 4, right? So level 5 has only one root of unity on which you need to do things. Level 4 will have 2 roots of unity on which you need to do evaluation. And in a sense, the operation that's happening is just this left leaf, if you consider them as a vector. You're just doing a linear combination of them with the right side using these two scalars. Okay, why am I talking about them in this combined sense? Because this is essentially what gives us the picture for how we are going to pack things together, how we're going to combine these values and do a combined computation on them. And so how do we pack them together? The key observation is, all the things that you're computing on with the other things, of course, you can pack them in different vectors. That is a prime necessary. But to be able to do this computation on top of shares, and that too locally, because ultimately these are all linear operations, right? The key observation is that you need to pack these values as far away as possible. Okay, so by that I mean, you pack like A1 with something which is a left component, but then it is like as far down this, sequence as possible, so that you're able to do local computation on them for as long as you can. So it turns out like the best or the farthest that you can pack them is by taking m by l plus 1 as the next vector, essentially. So that for this example would be that, you pack A1, A9, and then shift it again with the same value. So A17, A25. This is how you would end up packing. Okay, so this is like something you may not be able to see right now, but if you just like, I'll send across the slides, and if you stare at it for a while, you'll realize that any other push you can't do to this packing. This is the optimal way in which you can push things down. And then, as I pointed out before, the level 4 computation is just doing computation on these vector of values together using these scalars, right? So it'll be like a local computation on the shares corresponding to these pack vectors. But unfortunately, in spite of the farthest that we pack, you can only do this local computation up to a certain point in this recursion. So specifically, you can only go up to log m minus log l levels, which is in this example 3, just to give you how it's done. But after this step of computation, all the things that you would need to compute on end up being in the same vector or end up being within the share of the same vector. So you would need to open up these shares and, essentially do the computation on opened up shares or rearrange things. So this is the messy part. If we were able to go all the way down this recursion without needing to do this by some way of packing, this problem would not have arisen. So this remaining log L levels, right? Even though you've reduced the input size in some sense already by doing these computation, you still need to figure out how to do these remaining log L levels of computation. And that is what necessitates the king server. So the really choice we had here is either, ensure all of them get the split of work, but then a lot of communication goes in, which means that log L rounds of communication need to happen. And that's really bad if you look at the, practical scenario. So the trade-off or the practical solution that we adopted here is to use a king server. So let me tell you how you would end up doing this. So let's say you went all the way here and you are at this, this particular level where you have the specific values from, these level and want to continue doing this operation, right? So the key observation is FFT is like a linear operation. And this is good, which means that, you can use some form of a pre-processing of this form where you have some, shared random values. And you do like these last 2 layers of computation on these random values to get this. Why all this? Because we want to retain the zero knowledge component, right? When you're making use of things for the king server, you have to mask and give it to them. Otherwise, you'll essentially be giving secret value, and the single king server can get essentially the witness. So this is something we don't want. And all this pre-processing is to ensure that you're able to mask the value before giving it to the king server, who can then compute the remaining layers and then give you back the value. That's the high level. So once you have this, related masked value, you can, as each party, whatever shares they have, they will just mask the shares at the end of this level 3 and send it to the king party, who then reconstructs this. But minded. Now the value is hidden by this random padding. And the king party can do the local computation of level 2 and 1, which is the final 2 layers, and send it back. Okay. So the final step would be just obtained by, or the final value would just be, values would be just obtained by unmasking using these SIs. And the reason you can do this is because of this linearity here. Okay, so you can mask things and then unmask them later just because of this linearity, essentially. So this is like really a high-level picture of where you would need the king server. So as you're seeing here, the king server needs to acquire all these shares again from all the parties and then do these, computation. It is at this point reduced in size, but not really, because in FFT, you have this trade-off between the number of polynomials for which you're doing versus, so at the end of the day, you're doing M evaluations, right? At each level, you have M values. So FFT is still doing, essentially, the king party is still doing linear in the number of field operations. Yeah. Does that make sense?
Yeah. Yeah, it makes sense.
Yeah, so this is the reason why, because of FFT and the specific feature of it, with Pack Secret Sharing, we at least didn't see how to go beyond this barrier. And that's why we need the king server, essentially. Yeah, so hopefully I depicted both the aspects of the work, the one that helps us get like a great divide using Pack Secret Sharing, and then one that necessitates this asymmetry in some sense in the model. And partial products is something we have in the paper, which you can look at. And if you understood this, then Pack Secret Sharing essentially does help in a similar way for the partial products as well. Okay, so with that, I just wanted to come to the implementation part and tell you more on the numbers that we get. So this is a specific setup that we used where the local prover we compare with is like a 4 GB RAM system. And for the zk-SaaS service, the king server is the only one that needs, high power. So it's a 128 GB RAM. But all the remaining ones can be like commodity laptops and in fact have lower power than what we gave to the local prover, which is they're all 2 GB RAM each. And I want to highlight here that because of Pack Secret Sharing, in our model, which is again unique to our model in comparison to EOS, is the more the number of servers we use, the better is the benefit, because you'll be able to pack more things together. And so as N is larger, in fact, for smaller instances of N, we won't see any benefit. This is just like because of how Pack Secret Sharing works. So we really go at it with respect to larger Ns, and the more servers you engage, the better it is.
So I had a question on this that I was actually waiting to ask, because I'm assuming you're at some point, but I guess one dimension that seems like it could be a trade-off is bandwidth, right? I think how does bandwidth, I guess, to what extent does bandwidth become a constraint?
I have a graph on it.
Great.
But essentially,
so
I have a graph on it. Yeah. So I'll show you just shortly, and then we can talk more when I get to that. Okay, so the first set of graphs is just to show you, how far we can go in terms of constraint size and really how the time gets divided. The setup we take is that you take 128 servers to do the computation, and the packing constant is 32, and the number of corrupted servers proportionately will become 31, which means the adversary can take over 31 servers. For this particular setup, firstly, for memory exhaustion, we already see that the weak servers, or essentially the smaller ones, can already handle 16 times more constraints than what like a single local prover can do before running out of memory. So this is good. So as you see in this line, the orange lines correspond to the local prover and the time they take. And if you see here, this orange line stops at somewhere 2 power 20 for Groth 16, whereas the blue line, which correspond to the zk-SaaS, can go all the way up to 2 power 25. So we can handle more constraint size before you run out of memory. And in terms of running time, if you see, this is what I briefly mentioned when I highlighted our results, we get a 22x speed up over the consumer machine. So I kept saying that, the divide that we wanted to get was by the packing factor, which is 32 here. So why not 32x speed up? And this is something probably you already guessed. One is, of course, the FFT, because you don't get complete equal division of work for FFT. But there's also one more reason, which is something to do with partly both implementation and something we haven't figured out theoretically as well, which is we don't push for or we don't have the implementation with the Pippinger. So when you're doing this MSM computation on shares, we did not figure out how to do the distributed Pippinger algorithm for that step. So that's why, like, when the MSM is done locally, there, of course, the Pippinger is being done. So it's not like a complete split in that sense because of this optimization. It's something that we believe can be done, but we didn't do in this implementation number. So that's why, like, the speed up is lower than what we expected.
And to what extent, I guess, like, what's the breakdown between 1 and 2 in terms of the possible improvement? I guess even if you did a perfect Pippinger, or optimal Pippinger, you'd still not get to 32, right? So I guess, but how?
Yeah, you'd still not. Right. But it would really help because it's still like on the group operations that you get some improvement. So like you might still do much better than working on with the FFT stuff. Like essentially the FFT stuff is something that will play a role more in the sense of how much more you can tolerate before the memory gets exhausted. But really, in terms of the number of calls and how specifically for these protocols, right? MSM is really dominant. So that's what I was going to get at here. If you see the graph, the red component in these bars are essentially indicative of the group operations. So like the major part of the computation time is the MSM computer. And the yellow component is the field operation, which includes not just FFT, but all the other things. So that is also why, in spite of not getting a full divide, we are getting, in spite of it, like a 22x speed up, because MSM is like getting split. So if you do the Pippinger, I'm guessing like the improvement will be like nicely a little bit more. It's not going to be like just a very small improvement is what I was getting at. Yeah, so this is something we don't incorporate here in the implementation. Yeah. And this is the, in terms of bandwidth, if you have like different bandwidths, this graph just depicts how the speed up varies. So if you fix the constraint size to 2 power 19, which is itself like large, and as I said before, the packing constant and the number of corrupt servers continues to have this relation. So this is the optimal setup of L that we take, which is n/4. And for this, if you see, so the I want to stress here that the communication that happens, we don't do communication of every server with every other. So the topology of communication that happens is going to be just a star topology, by which I mean all these small servers only end up communicating with the king server. So you don't need every server to talk with every server. So that really saves up on a lot of it. And in fact, the choice to keep a king server for the FFT, instead of having something where every party needs to talk to every other party, was like a conscious choice to avoid this, slow down.
I see. So the king server's role in this protocol is not just the FFT computation; it's also effectively the primary node where everybody communicates with. It's almost like a coordinator, effectively.
Yes, exactly. And this is something that naturally appears in the MPC protocol for the other operations. Just for FFT, it's something that you can't even do without. Like, you need this one party to do the evaluation. But for the remaining, like, you can make a choice. But having the star topology really improves upon your time, because the communication, like the topology of communication really affects, right? So if each person needs to talk to each other person, there's a lot of wait time. So the overall clock time really blows up in that case. Yeah. So that is something just
I guess
I wanted to point
these
out.
graphs almost make me wonder if you increase the number of parties even more. I mean, it seems like basically what the graph implies here is that you're continuing to get improvement as you scale up. You can sort of see it's starting to, I would assume at some point it levels off because of the bandwidth. But like clearly, I mean, 128 is, you're still getting improvement. So I'd be curious to see what you like if you had 256 or even 512.
Yeah, definitely. Like it would be good to so like I said, that's I think the good part about this model, in addition to, of course, the intricacies of whether the client is online or not. That's the other difference that I wanted to point out with the EOS. I think like because of the way that MPC works, it works better for like a smaller number of parties. So when you have like 2 or 3 parties or 2 or 3 servers doing the delegation, EOS already gives you that speed up. Whereas in our case, like something like even eight servers won't be helpful.
Yeah.
Because
I guess
packing
it's just
constant reduces. Yeah.
the if you think about how mining pools work in like Bitcoin, for example, right? Typically there's a large number of smaller servers, right? And you can imagine the coordinator of like the mining pool operator could be the king server effectively, and then you'd be able to turn a Bitcoin mining pool into a proving pool in this model based on the fact that you can have a lot of parties, which is kind of interesting.
Right. Yeah. So that's really the takeaway, as I would put it. So I just wanted to conclude with some interesting directions which already were, I think, brought up during the course of the talk, but just to summarize. So of course, like the one natural question here is to get rid of this king server. And as you pointed out, like way ahead in the talk, Alex, you can use like essentially non-FFT based SNARKs and try to build zkSaaS for it. So this is something we're working on as follow-up. And it's an interesting thing to do. And this will not only help us divide perfect divide of work, but also split of memory. So it would help us, get to much larger constraint sizes before we run out of memory. So that's really the goal with the follow-up. And of course, like malicious security, as I said, can be handled. It's just that we don't have an implementation explicitly for that. But it's something that's at least not a roadblock for us directly in the head in sense of the theory sense. So we don't have an implementation for it. So getting to work it out for the malicious security is also like interesting to have as an implementation. And of course, like, as I said, I didn't focus on the aspect where the extended witness was itself shared by the client and how do you patch everything together and make it work for end-to-end applications. This is interesting. And in fact, this is something work in progress where this company is helping us, or rather like they were interested in actually building out something targeted to applications of their need. And this is like really work in progress now, but their goal is to build zkSaaS for Groth 16 and in the end-to-end sense. So I have everything set up, including the extended witness, and make it work like a service.
What would I guess, what's the circuit? Because Gracia, you're hard coding it, I guess. So do you know which circuit they're implementing?
Yeah, so right now I think the test versions are working for like hash functions. They're just working with like a bunch of SHA.
Got it.
But I don't know what they're like all the use cases for which they would need it. I don't know. But that's the test case for it.
Yeah. I was gonna say on that front, like to me, I think the one interesting, especially given like this work reminds me a little bit of DZK, and I think you obviously talked about a little bit how it builds on it, and you kind of have more privacy in this model as the client.
Right.
But a DZK, part of that direction, the interest in that research was around being able to compute gigantic circuits. In fact, I shared in the chat here, so this may be interesting to you and your co-authors. This is a Z Prize. We did a competition for a Plonk, so using Plonk to compute DZK, or rather a DZK style model for Plonk for a huge circuit. I believe it was 2 to the 28th in this one, 2 to the 28 in this one.
Right.
And that, I think, for applications, I mean, one obvious application area that I could see for this is zkML type stuff, right? So even relatively simple models in the ML world, like even classifiers, are huge when implemented in circuits. And so I think 2 to the 21 is probably several orders of magnitude too small for that. But if you could get and this might actually be a case in which you would want to get many more machines. Right. If you weren't suffering, like if you were still getting speed ups up to like 2 to the 9, 10, 11 machines, then you could implement some very complex machine learning stuff, and and have it be practical, while not having to obviously in the client the advantage of that over DZK is the client doesn't have to reveal the all of their private information, right? So that would be. If you guys are interested to, if you want to think about a motivating application for future work, I would recommend that one, because I think there's a lot of obviously there's a lot of interest in AI and ML right now. I think there's also a lot of interest in applying zk specifically to that area. So could be a cool direction.
Yeah, definitely. Yeah. So, I mean, that is a motivation for us to like, keep looking at this and improve in terms of like how much more constraint size we can actually tolerate using, making use of the power, all these servers completely, essentially. Yeah, it's an interesting work to follow.
And this is maybe a good point for those just watching or following along this, and then who are going to watch the video. I've pasted some links here, which the people on the, watching the video after the fact are not going to see, but zPrize is all about hardware acceleration for zk. There's a repo. Maybe I'll put a link in the video description, but there's like a lot of off the shelf things in there, like a very, very optimized MSM Pippinger algorithm for GPUs and FPGAs. And so for folks looking, to potentially improve what the work of, or implement this work, you can take some of that off the shelf.
Definitely.
And get some immediate, extra speed up.
Yeah, definitely.
All right, cool. Sruthi, this is great. Does anyone else have questions? Well, I guess I hogged the mic. I successfully hogged the mic and scared everyone else from asking questions. But Sruthi,
thank you so much. Yeah,
I really appreciate this is a great presentation, and I think really interesting work. It sounds like some exciting directions to take this in the future. Thank you very much for being here and for presenting this for all of us.
Yeah, thank you so much for having me. Yeah, this was a pleasure to talk about this. Yeah, thank you.
And I guess it's also worth thanking your co-authors for working on it with you.
Definitely.
To be here, but it's great to see. Hopefully you guys will be working on more stuff like this in the future.
Yeah, definitely looking forward to it. Yeah, thank you.